Welcome back to our study of calculus, and recently we've been having fun revolving various functions around axes, both on horizontal axes and vertical axes, creating volumes and using calculus to add up those little volumes and calculate the volume that a particular solid occupies. Um, what this chapter is, chapter 7, we're not going to add really any more calculus techniques. We're going to add some more functions. And I told you eventually we would get to this. So we could have put this chapter in various parts of the semester. We're going to do it kind of at the end. We're going to add more functions, and then we'll use this chapter as a mechanism to review some of our integration techniques like substitution and some of our applications, as in calculating volumes. But here you go. Here's the functions that you could handle, right? You could handle polynomials, right? And you could polynomials, meaning I can give you a function of x to the n or a sum of those. You would know how to take a derivative, how to graph, how to integrate. I could give you the sine. I could give you some trig functions, right? Sine of x, cosine of x, and tangent of x. You could draw those. You could integrate those. You could take a derivative of those functions, and also their reciprocal functions. But that's it. That's the list. Okay, so what are we going to add here? Well, we're going to add a few more functions. So first of all, in blue here, I guess we're gonna put some inverse trig functions. We're going to learn how to take the derivative of that guy, inverse sine, inverse cosine, inverse tangent. And then of major importance, shows up a lot, we're going to use this pair of functions, the exponential function and the natural log function. Okay, which all these functions are inverses of each other. So what we start off doing is talking about, well, what's an inverse? What is an inverse? And this is kind of a review. This section could have been part of chapter 1 when we talked about functions. But in general, an inverse could look like this. If I take a value x and I put it through a function, you might say, what do I get at? Well, let's call that y. If I take that output function and I undo it or inverse it, I get back out x. Okay? So remember that. That's what an inverse does. That's what an inverse does. If I could give you different notation, I could say what is the inverse function? I wrote down something like this of the function of x. Okay, well, this is another way of saying what? The inside there is y. If I put y through a function, through the inverse function, I'm going to get back x. This would also be the same as that's also the same thing as if I could say the forward function taken to the inverse of x, that's also equal to x, right? So I could flip these two functions here and I'd still get, they kind of undo each other. We could look at this graphically, and once again, I think you've seen this all before. You've seen this probably back in Algebra 2. But if you draw a function, to be careful to be able to draw a function that has an inverse. And I draw that function here, and the inverse of it, if this is f of x, the inverse has to be a reflection about the y equal x line. So if this is actually kind of a poor, say this function right here is y equal x. the inverse has to be a reflection about that line. So let me try to draw a reflection around that line. Okay, then this would be the inverse function. Okay? So graphically, you see that an inverse function and a function and its inverse have to be symmetric about the line y equal to x. That's one thing. Another thing they like to say is it has to be 1-to-1. In order for a function to have an inverse, f of x must be 1-to-1. What does that mean? For every x value, there's one and only one y value. Let me go to another line. Let me show you why what can't happen here. See, let's draw a typical function that doesn't have an inverse. If I look at a y equal x squared, this is not 1-to-1 because you can see for one there's two different, at x equal to -1 and x equal to 1, two x's give the same y value, right? This is 1, 1. This point over here is -1, 1. So there's two different y values that give the same x value. And so to do an inverse of that, if you would put 1, see if you put 1 into the inverse function, you wouldn't know which one to give out, -1 or 1. Okay, so in order for a function f of x to have an inverse function, it must be 1-to-1. This won't work. So what they might typically do is I will constrain the domain. Okay. Oh, well, look, that does have an inverse now. If I say y equal x squared only from x greater than 0, well, now I've defined a 1-to-1 mapping. For every x, there's one and only one y. And if I tried to, get a little idea of what that inverse looked like, maybe it would look something like this. Graphically, it looks like this could be the inverse of x. Y would be. Getting some intuition as to the shape is all well and good. How could I actually find it? Let me give you a mechanism for finding the inverse function. And this could work, I guess I would do it with this example first. Y equal to x squared. And the first thing I do to find an inverse is switch x and y. Switch x and y. So I would say now x is equal to, maybe I ought to do this in a different color, huh? I'm trying to find the inverse, so, and I even labeled that wrong, so that's good. This is not a derivative, this is the inverse. The inverse x. Let's do this in red. We're going to say x is equal to y squared, right? And then 2, we want to solve for y. Okay, and I'm going to get what? Well, square root of x is equal to y. So y is equal to the square root of x. These guys are inverses of each other. And it kind of looks like that, right? That function does look like the square root of x. We've been drawing things like that and rotating those curves now for a couple weeks. Let's try our functional block diagram method, see what that looks like. If I take a value and I put it through x squared, and then I run it through square root of x. Let's try it here. So you pick a number, x here, how about 5? Put a 5 in, I get a 25. Take the square root of 25, I get 5 back, okay? So you can see another demonstration. These functions are inverses of each other. Okay, as I said, we're going to be adding more functions to your arsenal to calculus so you can model more real-life situations. And here we go. We're going to draw our first one. Here is going to be an exponential function. Exponential function is, we're going to talk about e to the x. A special exponential function. This could be 2 to the x, 3 to the x, 4 to the x. E is Euler's number, right? E being equal to what? About 2.716, like that. Okay. What is the inverse function of e to the x? Do you know what that is? It is the, and if you would draw it here, see if I can get this right. This is the natural log. Very important functions that we'll use. That'll come up a lot. And I guess if I could go here, green. These are supposed to be symmetric, like mirror image across this y equal x function. And again, natural log and e to the x. You used to know your properties of exponentials. We got to relearn those, be good at those. Properties of logs, be very good at those. Maybe I'll just go through those in the next video. But those are places where people make their errors. And again, we can start to rotate these functions, create volumes and areas for these functions. We can take derivatives of these functions. We can model movement with them, and we'll show you how to do that relatively shortly. Okay. Besides those, these are the most important functions of the chapter. We do have our inverse trig functions also. And if we did that, let's see if I can get some drawings here. Here's the sine. And if you look, I'm just going to draw. You can see a sine function is not one-to-one by any stretch of the imagination. So as you might guess, we're going to restrict the domain just as we did before. This is the sine function, and then the inverse sine. The inverse sine, suppose it looks something like that. Inverse sine of x, or sometimes you'd see it written as the arc sine. And we have similar, there's domain and range requirements. Remember what a sine does though, right? The sine, when I say y is equal to the sine of x, maybe if I even put it through here. X, if I put an x to a sine, x is thought to be an angle, right? X is an angle. You take the sine of that angle, which is kind of gives you the y dimension of the angle as it goes around the unit circle. Gives you the y dimension. Okay? But x is an angle. Y is that height of the height of the opposite side of the triangle. If you put y through an inverse sine, the inverse sine is going to give you back an angle. So remember, this is an angle. So when you think about it, it could be, if it's in radians, it's going to give you an angle somewhere between pi over 2 and minus pi over 2. Okay, that's the range. That would be the range of the inverse sine. Okay, you could do the same thing with the inverse cosine and the inverse tangent. You take the trig function, you have to restrict its domain, the forward trig function, because in general it's not one-to-one because they're periodic functions. You restrict the domain and then create an inverse sign. I'm going to be honest, in general, these inverse functions do not come up as much in problems. But you have to understand they're inverse. We do need to know how to take the derivative of them. But if I was going to focus my time, I would stay over here in the natural log and exponential area. And but getting a quick review of the inverse sine, inverse cosine, and inverse tangent would be well worth your time. Anyway, that's about it for this video. I will see you soon. Bye-bye.